Over the past few weeks, I built a small automated test system to explore instrument control and sensor characterization. Specifically, I wanted to see how a light-dependent resistor would respond to red, green, and blue illumination. I wanted to gain hands-on experience with real-world test design, controlling lab instruments, synchronizing devices, collecting repeatable data, and analyzing sensor behavior programmatically. Using only components that I had laying around, I came up with a simple setup. I'm not getting any points for craftsmanship on this one. I really just dove right in and started building, figuring out the finer points as I went along. So here's the setup. An Arduino Uno controls an RGB LED in a small linear sled, which positions a photoresistor in front of the LED. My initial plan was just to move the sled manually in between each measurement. But then I decided it would be way more cool if my control script could take care of this for me. This took a few tries, but eventually, using a shoelace and an old cork, I got it working pretty well. The actuation mechanism and motor themselves don't really matter, since the program is designed to just start the motor and then keep it running until an infrared sensor detects that the next stop mark has been reached. So that's movement taken care of. Now for measurement. I used an oscilloscope to measure the voltage across the light-dependent resistor. A Python program runs on my laptop and acts as the master controller. When the Python program sends a trigger over serial, the Arduino advances the sled and then flashes the LED through red, green, and blue. Every time that a color pulse starts, the Arduino sends a handshake message back. That's how the computer knows exactly when to take the measurements. The project actually started in LabVIEW, which is the industry standard for controlling this type of test. But after playing around with it for a few hours, I wasn't really able to get the drivers working and decided to pivot back to Python. So my Python program handles both serial communication with the Arduino and SCPI commands over TCP to the oscilloscope. In my first measurements, I was getting all sorts of different values because of noise in the system. I dealt with this in two ways. First, I used high resolution mode, which is built into the oscilloscope, to reduce noise on each measurement. Then, I took 6 measurements for every pulse of the LED, which allowed me to take a longer average in my later analysis. These measurements were saved to a CSV, and I used Google Sheets to analyze them later. From the data I collected, I could calculate the effective resistance of the light-dependent resistor at each point. Since the LDR's resistance decreases with light intensity, higher measured voltages mean higher sensitivity. The trends are pretty clear here. Red pulses consistently produced the smallest voltage, green was in the middle, and blue gave the highest voltage. That tells us that this particular LDR is most sensitive in the blue part of the spectrum, which is the highest energy band, exactly what we would expect. By averaging across multiple samples and trimming the outlying values, this script gives us stable, repeatable results that confirmed some interesting things. We see here the results from one of the runs. We can see that the blue output consistently reduced the LDR's resistance the most and red the least. These points have been fitted with an inverse square graph, showing how the intensity of the light drops off with distance. As the distance between the sled and the resistor increases, the cross-sectional area of the light cone at the point of the light-dependent resistor increases with the distance to the power of 2. So we can see that this behavior is reflected in the results, with the effect of the LED on the photoresistor dropping, since the total light is spread over a larger area. I think I achieved what I set out to with this project, particularly the designing, building, and automation of a test rig that provides consistent, usable data. There's definitely a lot more testing, refining, and analysis that I could do with this, but for now I think I'm going to move on to some other projects that I have planned. Thanks for watching. You can find all the information on this and other projects, including the link to the code on my GitHub, on my website, which is linked down in the description. I'm going to be posting about lots more projects coming soon, so subscribe and hit the bell icon if you'd like to be notified when these videos come out. Till next time, have fun building.